In this video, I will be discussing another type of first-order differential equations. These equations are called homogeneous equations. So what is a homogeneous equation? That is an equation which can be written in the following form. So as usual, we have derivative dy over the x here, or equivalently, this is also denoted by y prime. And the right-hand side is a function of the ratio of y over x, meaning that somehow we can rewrite the right-hand side that involves the ratio of y over x only. And whenever we have such an equation, we have a homogeneous equation. So how to solve homogeneous equation? We will introduce a new variable. Introduce a new unknown, v, and we set v to be y over x, the ratio. So this would imply that y equal to v times x. So by introducing the new unknown v like that, the right-hand side here, we know that it's a function of the ratio, so it becomes a function of v. On the other hand, what is the left-hand side? Left-hand side is derivative dy dx. So let's compute this. Remember that y here is v times x. And we think of v as a new unknown, which is a function of x. So by the product rule, dy dx will be dv dx times x plus v times derivative of x in terms of x is 1. So then the equation, the original equation, can be rewritten as one side we have dv dx times x plus v, and the right hand side is a function of v. Then it turns out this new equation is a separable equation. As a new equation is a separable equation, which we already know how to solve. So after we solve for v, we will go back to get y over here, which is v times x. So by multiplying v by x, we get y. So let's look at a few examples of how to recognize homogeneous equations and how to solve them. For this problem, we want to solve the following initial value problem. So we have a differential equation x times dy dx equal to y plus x times cosine squared of y over x. And we have initial condition y of 1 equal to pi over 4. As usual, the first one is the ODE. And the second is initial condition, which says that when x equal to 1, y equal to pi over 4. So how do we solve this equation? As usual, we first try to isolate dy dx. So we want to rewrite the equation in the form dy dx equal to something. So divide both sides by x. Then what do we get? We divide through by x, and the first term will become y over x. The second one is x cosine squared y over x, but then we divide by x. So what happens is that the x cancels out, and we have just cosine squared y over x. So after doing this, we see that this is y over x, and this is cosine squared of y over x. What it means is the right hand side here is a function of y over x. And because of this reason, the equation is a homogeneous equation. So our ODE is homogeneous. So to solve it, we're gonna put v to be y over x. And as before, we have done that y is v times x. So by the product rule, dy dx is dv dx times x plus v times 1. We have done this above. Now, we're looking at the original equation. Here, whenever we see y over x, we're going to replace by v. And whenever we have here dy dx, we're going to replace by the expression over here for dy dx. Let me make a box around that. Yeah. So the equation, our ODE becomes, on the left side, we have dv dx times x plus v. And on the right hand side, as I already mentioned, whenever we have y over x, here we should replace by v. So the right hand side is v plus cosine squared of v. V plus cosine squared of v. Now simplify this. It turns out that we cancel these two, and we get dv dx times x equal to cosine squared of v. Now solve for dv dx. We have cosine squared v over x, and this is a separable equation. Separable equation. Which means that we can separate v and x. V is on one side and x is on the other side. So to do that, we could divide both sides by cosine squared. So we have something like this, dv over cosine square v. And then on the other side, we have x dx. Now we can integrate both sides. Right, so dv cosine squared v here equal to the integral of 1 over x dx. Well, the integral on the right hand side is easy to do. That's natural log of absolute value. And as usual, we add c here. What about integral of 1 over cosine squared v? It's a little bit tricky. You need to remember 1 over cosine squared is secant squared. And then what is the integral of secant squared? This is tangent. So we have tangent of v is natural log of x plus c. So let me recall the formula. Integral of secant x is tangent x plus a constant c. So we should have added the constant c here, what I said in the previous topic. We only need to add c on one side, because if we have c1 on the left, c2 on the right, we can combine them into a single c. All right, but let's go back to y. What is v? V is right here. V is y over x. So we have tangent of y over x equals to natural log of x plus c. We are given initial condition. So let's use initial condition. We say that x, if you recall, we said that x equal to 1 and y equal to pi over 4. So we plug in, we have tangent of y over x, which is pi over 4 equal, divided by 1 is the same as pi over 4, natural log of 1 plus c. Natural log of 1 is 0, and what the tangent of pi over 4? You know how to do this. This is just 1. So c is 1. And then we plug c equal to 1 back into the above equation right here in order to solve for the unknown y, which we are looking for. So we get tangent of y of x equal to natural log of x, natural log of absolute value of x plus 1. So how do we solve for y? Tangent of y over x is whatever on the right hand side. So y over x is arctangent of whatever on the right hand side. And now multiplying both sides by x, we have the final answer x, y equal to x times arctangent of log of absolute value of x plus 1. And this is the solution to the given homogeneous equation. Now, let us discuss another example. Solve the differential equation, the ODE. So this time we don't have initial condition, and the equation is written like this: x y prime equal to y squared divided by x plus y. As before, we need to solve for y prime first by dividing both sides by x. So the numerator is still y squared, but the denominator we have x and x plus y. which can be written as y squared divided by x squared plus xy. Now, how do we know that this is a homogeneous equation? It turns out that whenever we have a fraction, uh, and we have several terms in the numerator and denominator here, circling. The degree of this is degree 2. Degree of x squared is also 2, and degree of xy. If I'm looking at the total degree, we have x to the first and then y to the first. So the total degree, which is just the sum of 2 degrees, will be degree 2 as well. So if we have a fraction and every term has the same degree, then we will have a homogeneous equation. So how to see that? Everything has degree 2. Let us divide both numerator and denominator by x squared to see what happens. So what we have is this. Numerator is what? Y squared, and we need to divide that by x squared. In the denominator, we do the same thing. We need to divide everything by x squared. So we get x squared divided by x squared plus xy divided by x squared. And then we simplify this. The numerator can be written as y over x squared, and in the denominator, x squared cancel with divided by x squared, we get 1, and then xy divided by x squared becomes y over x. So you see that the right hand side is a function of the ratio ratio y over x. And that's the reason why the equation is homogeneous. We see ratio of y over x here. Okay, because the equation is homogeneous, we can solve by putting v equal to y over x. And as before, y is v times x. And so by the product rule, pram or dy dx is just dv dx times x plus v times 1. And of course, y prime here is nothing but this is the same as dy dx. Something. Now the equation, our equation becomes the left hand side is dv dx times x plus v. And what is the right hand side? The right hand side, whenever we see y over x, we should replace by v. So what we have on the right hand side is numerator is v squared, denominator is 1 plus v. Now we have a new equation with unknown v and independent variable x. First, simplify this. On the right hand side, we have v squared over 1 plus v minus v. Using the common denominator, we have 1 plus v in the denominator, and then v squared minus v times 1 plus v. Distribute and simplify this. We will get minus v over 1 plus v. Still on the left hand side, we have dv dx times x. So in this, we have a separable equation because as before, divide both sides by x, we have 1 x here, and then minus v over 1 plus v, and we can separate the equation. This is separable. And this is always the case whenever we have a homogeneous equation and we introduce the new unknown v being y over x. The new equation will be separable equation, and we can solve by the method of separable equations. So to do that, we could multiply both sides by dx, and then cross multiply, I should say, maybe easier way to do. Cross multiply. We have 1 plus v over v. There's a minus sign, but let me put the minus sign on the right hand side. So cross multiply, I will have this. Or cross multiply in a way to make sure that the equation is separated, one side for x, one side for v. And now we're going to integrate the 1 plus v over v dv equal to the integral of 1 over x dx. Oh, sorry, there's a minus side. I forgot that minus side. The minus side. The minus side comes from here. That I keep it on the right hand side. So the integral of the right hand side is easy to do. It is minus natural log of absolute x plus c. What about the antiderivative of the left side here? How do we do that? You can pause the video and try to do it. What we can do is to divide out. So we separate 1 plus v over v becomes 1 over v plus v over v. And so we have 1 over v plus 1 dv, and the right hand side we still have minus log of x plus c. Now once we have written into this form, the antiderivative is easy to do. That's natural log of absolute value of v plus v equal to minus natural log of x plus c. Now how do we get back to y? Recall that v is y over x. Right? So whenever we have v, we should replace by y over x. We have natural log of y over x plus y over x equal to minus natural log of absolute value of x plus c. At this time, we cannot solve for y. So this can be left as the solution. So we have an implicit solution. it turns out that this solution can be simplified a little bit more. Because we have several log together, so we can simplify by moving the minus log of x to the other side. We have log of y over x, and then combine with log of x plus y over x equal to c. And what is the rule for log of, or the sum of two natural logs? It's just natural log of the product. So y over x times x, that's the rule of logarithm. And then we can cancel the x, and we get a better look solution in which we just have a natural log of absolute value of y plus y over x equal to c. And this is a general solution, but implicit solution for our differential equation. General implicit solution. Now, so far we have learned several type equations. The difficulty in solving differential equations is that we need to identify the type of equations to use the correct method. So here I'm gonna just describe a little bit the strategy of how to choose the correct method to solve. So recall that a general first order equation is always of this form: dy dx equal to an expression in x and y. It could be a complicated expression. So whenever we have such an equation, how do we solve? The strategy that I would recommend you to do is this. First, try to factor the right-hand side. If we can factor, if we have like this, we can factor as something like g of x. We can factor completely as a function of x times another function h of y. Then we have separable equation. And once we have separable equation, we can separate and solve. So first step is to check for separable equation. Second step, if it's not separable, then we check for linear equation. Is it a linear equation? How do we know? Try to rewrite the equation in the form y prime first, or dy dx. I'm going to write in that format: dy dx plus px y equal to qx. So for linear equation, you only have two places where you see y. The first one is dy dx, and the second one is just some coefficient times y alone. If you have something else like y squared or cosine of y, definitely the equation is not a linear equation. Or at the same time, when you check for linear, if it's not linear, but it turns out to be a Bernoulli equation. Then the format is quite similar to linear. It's almost the same as linear equation. So I write in this way, bx times y. On the other side, we have cx together with a power of y. Almost linear, but we have y to the n here. That's a Bernoulli equation. So to solve a Bernoulli equation, you should look back at the topic about Bernoulli equation. And lastly, if we don't have any of the above, then it's likely that the equation is homogeneous. Of course, there are other types that we will learn later as well. But for now, not one of the above, then maybe homogeneous equation. And one way, as we have seen in the previous in the example, one way to recognize homogeneous equation is like this. We have a ratio in which the total degree of all terms, the total degree of all terms are the same. So you look at the terms in the numerator, the terms in the denominator, all of them have the same total degrees. We saw that earlier, but for example, something like this as well. If we have something like this, it's also homogeneous. So x y squared plus y cubed plus x cubed over 2x cubed plus yx squared. Then we have a ratio on this side, and if you look at all the terms in the ratio, so in the numerator we have these things, and denominator we have these things, and each term has total degree 3. As you can see, it's x to the first and y squared. So the total degree is degree 1 plus degree 2, which is 3 total. Degree y cubed, total degree 3, x cubed, same total degree here also 3, and then yx squared, we have y to the first, x squared, so total degrees are always 3. So in that case, we can divide both numerator and denominator by x cubed. So divide all by x cubed. Then you will have something dy dx equal to the first thing divided by x cubed, the second one divided by cube, and then x cubed divided by x cubed. We need to do the same in the denominator as well. 2x cubed divided by x cubed, and then yx squared divided by x cubed as well. Simplify things. We have that y squared over x squared, and then y cubed over x cubed plus 1. Denominator, we have 2 plus y over x. So we see that everything here is can be written as a ratio of y over x. This is y over x quantity squared. This is y over x quantity cubed, and so on. So this is the homogeneous equation, and we can solve by putting v equal to y over x. Now, don't try to solve it. This may be difficult to do, but just wanted to give you an idea of how to recognize homogeneous equation. And this is the end of the lecture for homogeneous equations.